Off the series before getting to the weeds and details that can get very quickly complex and confusing. I wanted to show the bare minimum setup of what we'll actually need to spin the motor on the car. So then together we can go on this journey to gradually building up the complexity of the car to meet rules requirements and justify our own design choices along the way, give you a better idea of how 2023's car was designed. Taking a quick look at the general layout for the chassis and accumulator wiring, we see how complex this system is, which is why I want to approach things in a common sense and systematic way so you can understand how the system truly works and how it was intended to function. Today we're going to build out this blank chassis so we can truly go over every step of the car so this car will be familiar to you as it is to me. As we go along building out this chassis, we are correlated to the appropriate rules and requirements for competition. This is important as well point out where we succeeded and failed in our design so you can learn from our past mistakes and make future EVs for global motorsports successful. Let's start with the basics for how we will run the motor. For sake of clarity for this explanation, I will cover the motor controller and the motor in more detail in another video about each of their specifications, how they function, and why they were chosen. In this diagram, this is an idealized setup with several assumptions being made about the current state of the motor controller, and if it's happy enough to want to run and spin the motor. I'll refer to this as our drive ready state, so any signal applied to the throttle will spin the motor accordingly. Though there are some requirements we'll need to meet in order to be in the drive ready state. First off will be the high voltage is connected to the motor controller, so it can obviously supply power to the motor. Second is a low voltage connection. This is typically between 12 to 14 volts, which will power all the logic to the motor controller. Third is the motor controller is obviously connected to the motor. This is a 3-phase motor, so it will have 3 wires that will go to the motor controller, which will supply power to it. Additionally, there is a temperature sensor on the motor, which goes to the motor controller, which will go to the motor temp pin or analog input, which that kind of brings us into the fourth requirement, which is the 4 signals that you see that are labeled or that have the brown wires going to the motor controller: the throttle signal, the brake signal, the forward enable, and the motor temp. These signals are necessary for it to be in the drive ready state. So the 3 analog ones are the throttle, brake, and motor temp. The throttle and brake are you basically just apply a variable voltage from 0 to 5 volts, which will then correlate to the proper speed and brake signal. The second is the motor temp, which is again analog voltage, which will actually come directly from the motor itself, which are 2 wires, one for power and ground, which could connect to that, and then 1 digital input, which is the forward enable, which basically tells it that it will spin in the forward direction. Here is a quick example of how to hook up one of the analog signals. We'll start out by looking at the datasheet for the appropriately named pins. In this case, we'll cover the accelerator panel. We'll be using pins 1, 13, and 2. Pin 1 being the 5 volts, which will power the analog circuit. 13 being the accelerator pedal wiper, which is where the variable voltage will be applied to, which will gauge the speed of the motor. And pin 2, which is the pedal ground, so we'll be providing the ground for it to complete the circuit. Pin 1, or excuse me, one of the easiest ways to do this is by using a potentiometer. So pin 1, you can simply put 5 volts to the first terminal on a potentiometer. Pin 13 for the accelerator pedal wiper, you can apply that to the second terminal of the potentiometer and ground on the last one. So now whenever you spin the knob on the potentiometer, it will vary the voltage and just varying the speed of the potentiometer, or varying the speed of the motor, excuse me. In the datasheet, though, for the motor controller, they have a recommended analog circuit that they suggest you use if you're going to utilize analog inputs. This is basically the same of what I showed you previously, except they have a resistor on the ground side as well. And basically what this will do is it will keep a constant voltage for, instead of going from 0 to 5 volts, it will stay between 50 millivolts to 5. And this is because it actually reads 0 volts as a fault state or as a short circuit. So there's just a little bit of an offset, if you would, provided for the analog pins just to account for that possibility of a short or some other thing going wrong with the analog signal. Now we should be ready to go and spin the motor, right? Well, yes and no. Remember how we assumed that for our purpose that the vehicle was in a ready-to-drive state? There are actual several states we need to go through first in the motor controller startup sequence to get there. In addition to that, we need to be running coolant, in this case water, through the motor controller as well to avoid damage to the controller while we run it, mostly from overheating. And lastly, we will need a discharge circuit so when we unplug the high voltage, we can discharge any remaining energy that remains in the motor controller. Let's take a look first at the vehicle state machine and what we need to do to get it into a drive ready state, which is going to be state 5. Our first step is to start state. There are two different start states for our motor controller which the user can choose in the configuration settings. The first one is relatively simple, where all you need to do is simply apply power to the motor controller for it to go into state 0. The second startup sequence is actually something more similar to what you would experience in starting up a regular car. You will first need to have a switch, which is when you turn it on will supply power to the motor controller, and another pin called ignition. In this case, when you apply power to the motor controller, it doesn't instantly go to state 0. You actually need to press the start button, which is another pin on the motor controller, which when you press it, it should apply power to that pin. So when you have this button hooked up to the start pin, when you press it, it will then go into the motor controller state 0. There are some finer details to the startup sequence, which for time's sakes I'll pass over, so please read the datasheet to get a full understanding of how this startup sequence works. Now that we have gone into state 0, the motor controller will now attempt to go into the next state, which is the pre-charge. The purpose of this is to engage the high voltage to the motor controller. Though instead of directly connecting the motor controller to high voltage, it actually first goes through a resistor. The purpose of this is to protect the motor controller and give the capacitors inside the motor controller time to charge, as the resistor will limit the current to the motor controller when engaged. There is a dedicated pin on the motor controller specific for powering a relay, which will engage the high voltage through this path. Once this pre-charge is done, and when we actually want to start applying power to the motor to spin the wheels, it wouldn't be a good idea to keep a resistor in this path of the high voltage. This is where the main relay enable signal comes in, which is another dedicated pin on the motor controller, which will power another relay that will engage the high voltage to the motor controller. Only this time, though, not through a resistor. This will be safe to do because the voltage on the motor controller when disengaged from the pre-charge relay will still have the high voltage potential. It will be at the same high voltage potential it was. The only thing we're changing now is getting rid of a resistor in the pathway of the high voltage. For clarity's sake, let's run through the vehicle state machine as if we were actually trying to power on the car and run the wheels. So, starting with start state 0, whichever start state you decide to choose. For this case, let's choose the first one, which is the most simple one, just applying power to the motor controller. So we're now in state 0. As soon as we're in state 0, it is going to go and initiate the next state, which is state 1. So if this is for the pre-charge initial state, which will turn on the pre-charge relay. So on the pre-charge pin of the motor controller, it is going to send 12 volts to the pre-charge relay. In this case, this is one on the leftmost side, and that has the resistor in the path to the motor controller for the high voltage path. The charge time usually takes around like 1 to 3 seconds, depending on the resistor value that you choose. Check the datasheet for determining the right values for this, as you will need a fairly hefty resistor to handle the amount of power that will be going through it during that amount of time. Then once the motor controller is charged, it'll first turn on the pre-charge relay, go to state 2, wait for the capacitors to finish charging, then after that go into state 3, and if it determines that everything is good and that the motor controller is charged, it will actually switch off the pre-charge relay and initiate the main relay enable pin, which will send another 12 volt signal to the relay that doesn't have the resistor in the path going to the motor controller. And then we'll be in state 4. State 4 is now going to be determined by the forward enable. There's also a reverse enable as well, but for this case we'll just focus on forward because that's the one you're going to be using in the car. So forward enable is a digital signal, so it's going to be anything from 0 to 5 volts. So you can just directly tie it to 5 volts in this case, just so you can always have it on. Though just keep in mind when you're actually wanting to run the vehicle, you're going to most ideally want a switch just so you can enable that yourself. So once you enable forward enable, it will then go to the ready state and begin energizing the motor. So now when we apply that variable voltage to the throttle, it will start to spin the motor. In this example that we just ran through though, we assume that we did not run into any fault states, which is state 7. So whenever the motor controller detects a fault, it will instantly jump to that state and not do anything else until you fix that fault. There are a large amount of things that the motor controller will determine as a fault, which you can read in the datasheet. For this example, the faults that we could run into in this could be for the motor temp, the brake, or the throttle signal. The motor controller is a little particularly picky about the voltages that you need to keep the brake and throttle signal between. So check the datasheet for those voltages because it will give you more of a clear indication of how you should set up your circuit for that. As I just assumed for this example, just 0 to 5, but ideally when you're actually trying to use the throttle signal, it will actually go into a fault state at 0 volts for either the brake or the throttle signal. So you'll need to always keep it a little bit on. So using the analog circuit that the motor controller indicates is really helpful in this case. So you can have an offset to that and not go into a fault state every time you try to use the brake or throttle, say if you just have it set at 0 when really you need an offset voltage for that. Additionally, in this example, the motor temp can throw a fault if you have it unplugged. The motor controller is picky about this as well. You need to have that the motor controller or the temperature wires from the motor running to the motor controller to those correct pins so it can properly calculate the motor temperature while it runs. So in this use case, we ran through actually some of the fundamentals that we are going to need going forward to actually run and power the car. Though looking at the actual diagram of how our accumulator top section is hooked up, you can see some of these fundamental elements for activating the motor controller, such as the pre-charge relay and the resistor, and that main relay as well. That doesn't have a resistor in that path. Though you'll see some other things in this diagram as well, such as the lower interconnect. You see, there's another relay on the negative end of the high voltage path, and all these other little things that it interacts with, such as with the relay control board and the IMD. This will come in time as we go through explaining how the tractive system works, as really a lot of these things that you see here is really just for the safety part and meeting rules requirements. As we just went over, you could actually pretty easily run the motor just through the setup that we went through, though it's not exactly the most safest way, and it's definitely not rules compliant. So going forward, we're going to go step by step through how our top section is set up to meet rules requirements. Just always note though that the fundamentals that we captured in this video are going to be important to know going forward. So use this video as a reference for how the motor controller is going to actually start up, because there are a few finer details that we're missing at the current moment for how our top section actually works for powering those relays for the pre-charge and main relay enable that we talked about, though we'll cover that in the preceding videos.